Thank you so much. Thanks for inviting me, Sohail, and really excited to be here. Today I want to talk a little bit about some of the recent work that we are doing in our lab in the space of learning robot policies. So just one note, this talk is probably going to be more on the practical end of things. So I'd imagine like the type of talks you guys have seen in your seminar course has ranged from theoretical to practical. This is from a practitioner's view of how to use machine learning in the space of robotics, in the space of controls. And in general, just more broadly in my lab, I'm pretty interested in building robot policies, interactive robot policies that can work well with humans. So we are interested in tasks like assistive feeding, like how do we like get a robot to pick up a piece of food and transfer it to a person's mouth, or other types of interactive robotics tasks. And the type of work that lies in like that we are looking at fall into two categories. How can we use interaction data? How can we use human data to better learn robot policies, which is actually the topic of this talk. And then we are also interested in better, more seamless interactions between humans and robots. How can we do better shared autonomy? How can we get a human and robot to make a sandwich together? How do we go about these types of more coordinative, collaborative tasks? All right, so let me just get into the details of this talk. If you have any questions at any point in time, feel free to jump in. I'm not going to be looking at chat, but feel free to just like speak up. I don't need to go over all slides, so I can also stop at any point and can just have a discussion. Okay, so about like 2 years ago, we started looking at this problem of assistive feeding. This is one of my favorite problems, robotics problems out there. So what is the problem? The problem is I want to have a robot to be able to pick up a fork and pick up a piece of food and transfer that to a person's mouth, very much on the practical end. Okay? But it's actually a very extremely difficult robotics problem. Why is that hard? Well, part of the reason is that different types of food have different geometries, different deformabilities, and it would be really difficult to actually manipulate deformable objects. So that is like a whole research direction. And once you pick up the food, thinking about transferring the food to a person's mouth, that's also a very interesting interaction problem. How do we make sure that the food is easily transferred inside of the person's mouth? How do we put the right like forces? How do we think about the human's comfort? So in general, we thought, okay, so we can pick this and see what is the state of the art out there for doing this. So the state of the art for doing assistive feeding is to follow a fixed policy. So this is a model-based policy. The robot is basically doing some level of visual servoing. So it's going to basically look at like where the human's face is and try to like go to where the human's face is. And it computes a fixed pose and it tries to go there and ask a person to take a bite right there. And like, as you can see, this is incredibly like uncomfortable. I'm really thankful to this particular user who like sat there and allowed us to use this robot to transfer the food to a person's mouth. And in general, like, as you can see, not very comfortable, right? Like this policy is probably not like the policy that I would want my robot to have. So it turns out that this model-based policy is not doing everything right. And the question is, well, why? And could we do better? And one idea is, well, machine learning has addressed a lot of research questions in recent years. Could we use machine learning to actually address some of the issues here? So then if that is the goal, if our goal is to use machine learning, then we have a bunch of options, right? Like, for example, we could use reinforcement learning, but I actually don't want to run reinforcement learning in real, like with this person, like in the loop, right? I really don't want to hit the person's nose and like get a negative reward. That's not a good idea. I also don't have good simulators for any of this. I don't have a good simulator for a carrot. I don't have a good simulator for like a person's mouth. So it's not like I can just generate lots of data and run reinforcement learning in simulation either. So it feels like simulation and in general, like reinforcement learning is going to be difficult in this domain. The other idea, which I'd argue is more promising in the space of robotics, and I feel like there's going to be a paradigm shift towards that direction more and more, is this idea of collecting expert demonstrations and learning and imitation learning policy from those expert demonstrations. It feels like you're seeing like some evidence that giant transformers with large amount of data are going to be useful in many other fields. So the question is, could we use the same sort of paradigm here? Could I collect expert demonstrations and from these expert demonstrations be able to learn a robot policy for transferring food? So that would be wonderful if I actually had a lot of data. And in this domain, I don't have a lot of robot demonstration data. And I'll come back to this idea of robot demonstration data a little bit later in the talk. But in general, this brings me to this idea that maybe we should tap into other sources of data, right? Like if we want to learn some robot policy, expert demonstrations is pretty limiting. So maybe we should look at other sources of data like play or suboptimal demonstrations and leverage that information as a way of thinking about learning robot policies. And that's a topic that I'll be talking about in this talk. But going back to this problem of assistive feeding, it seems like at the moment, at least, the model-based policy is not that great. Learning doesn't seem to answer the question. So how do people use robots to actually do these tasks if those two are out of the picture? Well, the question is, maybe we could teleoperate the robot, right? Like if I can't use learning, if I can't use a model-based policy, the simplest thing I can do is I can use a joystick and I can teleoperate this robot, and then the robot should just follow my teleoperation input and transfer the food to a person's mouth. That should be the simplest thing. And there are like all these assistive robots out there and people use them. So that is probably what they do. And that is true. That is what they do. So here is actually a video of a person using a joystick to teleoperate a robot arm, open a fridge and try to like move items around in the fridge. And one thing to notice here is that even when you're teleoperating, which is the simplest thing, you are joysticking the robot, it is still pretty difficult to do these simple tasks at home. It takes forever to like open the door. Like it actually takes quite a bit of time for doing that. And you might be asking, well, why? Like I'm like joysticking the robot. I have control over everything. This is not doing anything intelligent. Well, if you think about it, this robot has 7 degrees of freedom or 6 degrees of freedom. And the way we control this robot is by using end effector control, meaning that we are controlling the pose of the end effector. And that means 6 things. I'm controlling X, Y, Z of the end effector, so the linear control. And I'm also controlling the angles, yaw, pitch, roll of the end effector. So if you guys look at like this person's hand, he keeps pushing the side. He keeps pushing the side of the joystick. And what that does is that he's changing the mode from linear control to angular control. And that is why it actually, like this mode switching is the thing that takes a lot of time and makes this task pretty challenging. So what I'm going to do in this talk is I'm going to actually start talking about teleoperation, right? Like this teleoperation also seemed like is not giving me the answer. So what I'd like to talk about is how we can build better interfaces using learning. How can we learn better interfaces where people can provide lower degree freedom actions, use language as a way of teleoperating this robot so we could actually get the robot doing interesting tasks in the environment. And then I'm going to switch topics a little bit, and I'm going to go back to this idea of learning a fully autonomous policy. So not the shared autonomy domain, but really the fully autonomous like domain where I just want to learn robot policies for various types of tasks. And here I want to tap into other sources of data like play data or suboptimal demonstrations. And at the very end, I just want to like end with some of the challenges of assistive feeding, some of the more model-based challenges of assistive feeding that these learning algorithms are not going to address, and the fact that we need to think a lot more carefully when it comes to exactly the problem of food acquisition and transfer. So I'm going to end with some videos and thoughts on that at the end. All right, so let's just get into it. All right. So going back to this picture, the idea that we have here is, if you consider a sequence of states and actions, and these sequence of states and actions, they can come from an expert or a caregiver. In this case, this is Dylan. He was a postdoc in our lab. He's now a faculty at Virginia Tech. And what Dylan was doing was providing these expert data. And what we would like to do here is we would like to develop a low dimensional action space that the person could use for teleoperating the robot, as opposed to these 6 degrees of freedom or 7 degrees of freedom. And the idea is collect expert data and try to bring the dimensionality of that using like a simple conditional variational autoencoder, and bring the dimensionality down to a low dimensional action space. In this case, this action space is Z. And this Z you can imagine it's a 2-dimensional, 2-degree freedom action space. So if you have a joystick, you would be pressing up and down on the joystick and left and right on the joystick. And the way that we make sure that we are learning an action that is actually reasonable is by training this autoencoder architecture that is conditioned on the state. So let's like back up for a second. So if you're thinking about the robot going from one point in the space to any other point in the state space, we actually do need like all those 6 degrees of freedom. And there is a reason that they exist, right? There is a reason that I have 6 degrees of freedom when I'm thinking about like controlling the end effector. But the key idea here is that if I'm conditioning this on a particular task, if I'm thinking about feeding, picking up a piece of food, there might actually exist a lower degree freedom action space that is sufficient for my task. So if I collect data for my task, then maybe I can learn that lower degree freedom action space. And in addition to that, like when I'm learning these latent actions, I need to make sure that these latent actions satisfy a set of properties that I care about. So these are things that we usually care about in control, right? Like these are things like reachability, controllability, temporal consistency. If you're pressing right, you would want right to have similar meaning in similar states. You might want your control to have some level of linearity, like scaling. So these types of properties are properties that you would ideally want your lower degree freedom control action to also satisfy. So when a person is using that, they would be able to control the robot and have like the same expectations from the robot. So we are incorporating these properties as a regularizer as part of the loss function when you're training this conditional variational autoencoder. So then at test time, what happens is that I can just take that decoder that I've trained and I can bring in a new user, a new human, using a joystick with 2 degrees of freedom using this latent action. And again, conditioned on state, I would be able to generate actions in this higher degree freedom action space. So that is the key idea of this latent actions work. So let's see what that results in. So here I'm comparing end effector control, where I'm controlling just the pose, the end effector pose of my robot, that 6 degrees of freedom thing that I was showing earlier. This is kind of like the state of the art on assistive arms. You can control X, Y, Z and yaw pitch roll. And on the right, I'm showing latent actions, this approach that I was talking about earlier. So here we are looking at a long horizon task of making a mock-up apple pie. And as you can see on the left, like the user is stuck in a mode and is having a really difficult time getting out of that mode. But on the right, you can like a lot more smoother, like move between the shelves, move objects around, just generally do the task a lot faster and in a much more smoother manner. And the time actually matters a lot to users with disability who usually use these types of arms, right? And this approach, in terms of the time that it takes to do it, it's much lower than, let's say, using end effector control. We also ran a user study here, and then we decided to like compare these approaches in terms of ease and predictability and adaptation. And in general, like our algorithm outperforms the end effector baseline. One interesting point here is that users actually don't like our approach, which is a very interesting point, because it is easier, it does the task, it is faster, it's more accurate. It does satisfy all these different properties that one would care about. But the thing that it doesn't satisfy is this idea of predictability, right? Like you being able to predict what the robot is going to do when you're pressing right on the joystick. And because it's a state dependent, like latent action, right? Depending on what state I am in, if I'm pressing right on the joystick, it actually means very different things. The robot is going to do very different things. It does the task for you to a good extent, but the meaning of it, the predictability of it is very much limited. And the users actually didn't really like the fact that they weren't able to predict what the robot is going to do next. So it was magically doing it for them, but they weren't able to, like the robot wasn't really transparent about what it was capable of. So I think this opens up a number of questions on the transparency side of things. So can the robot try to be more transparent when there's a human user sitting on the other side and trying to like make sense out of what the robot is trying to do? We also decided, yes.
Can I pause you? This is very interesting. So I was wondering, in fact, about like exactly this point that you mentioned, because then right and left or up and down doesn't really translate to like the physical directions. So is it possible that you perhaps like add another module, getting instructions from users and then spitting out the latent the latent variables that you need to feed into your basically the model?
Yeah, that's a very good question. So we have a follow-up work that try to do that to some extent. The way that we are doing it is not in all states. So basically, if you're pressing up on the joystick, the robot might do something. And if you're and maybe a different user would want the robot to do a different thing when you're pressing up. So we have like this follow-up paper where we are doing some level of active learning almost, where we are actively like querying users like and asking them, when you press up, where do you expect the robot to go? Do you expect the robot to go to this state or this other state? And based on that, you're basically aligning these like latent actions a little bit towards user preferences. But we did it in a simple way, in a sense that we mainly did this like at the initial states of the tasks, as opposed to at all these different states. So I think it would be interesting to do that like more generally, like and have like a better coverage of the state space and what the latent actions should actually mean. One other interesting observation is that like even though we do this, users tend to adapt to whatever it is, like kind of quickly. So they don't like it, but they adapt to it and they're able to use it. So that part of it is also pretty interesting to see in the user study results. But that's a good point, I think.
This is fantastic. And just to follow up on that, because this is very interesting. So what happens, maybe you have tried this, like, so, you know, basically letting users to control all the states, if they're like 6-dimensional or 8-dimensional, control all of them, but don't use the control, basically project it to the manifold of the smooth solutions that you basically train based on your previous data. Basically get that, then push it through the encoder, get the latent space, and then push it through the decoder. It's like kind of a projecting to the manifold of the smooth solutions.
So let me make sure that I got that. So basically this was during training, right? So during training, like an expert like Dylan in this case was providing like that data in the 6-degree freedom action space. And then like going through this, like we are basically having this 2-degree freedom on this lower dimensional manifold. Then at test time, we are basically telling users, hey, come in and just use that 2-degree freedom manifold that we just learned on Dylan's data. What you're suggesting, is it that at test time we would provide the, can you repeat that again? So what your suggestion?
At the test time, use the encoder as well. Basically, you know, let users to, you know, have, you know, or have this imagination that they have control on all of the states, S, and
oh, I see what you're saying.
And then push it through your encoder and then pass it through the decoder.
We haven't tried that. We have not tried that. That would be interesting. So like they think, like kind of like almost like trick them into like thinking that they have control over things. That would be interesting. In general, like making sure that we are aligning this manifold to people's expectations, I think is also just generally like a good idea. We have not tried that though. That would be interesting to try.
There's one question on chat. Let me just read it to you. So it says, how rich is the state context? Is it just the robot pose or also camera?
It has to encode like the state information of the world, so camera input as well. Yeah. So it's pretty rich. Yeah. Okay, let me go to the next. Okay. All right. Let me also see. There was another chat. Can we use causal models to learn interpretable latent states? That would also be interesting, something that we have not done. I do think in general, and again, these are latent actions, not latent states. So I just want to differentiate between that. These are action spaces. But yeah, again, like I would think that in general, interpretable action spaces would be really like useful in this domain. And we have not tried using causal models here. That would be interesting. All right. Okay, so moving along this, we also did some studies with users with disabilities. So this is a small study, so only with 2 users with disability. And in general, you can see that this approach gives us like a lot smoother types of trajectories. And again, it's faster compared to end effector control and so on. So what I've talked about so far is this idea that latent actions, it provides this intuitive and low dimensional control space so that users can just work in that lower dimensional control space. And then the robot almost autonomously figures out what should be the higher dimensional control to actually execute. So one can really think of this as a shared autonomy paradigm. It's a way of humans putting some level of work and then the robot learning how to like do the rest. And one interesting question to ask is how far can this go, right? Like, is this sufficient or can we use other types of data to actually make this, makes this a little bit better? So for example, right, like there was a question about like how rich should the state information be? And given that this is a state conditional latent action, if you're, for example, if you have a robot that's, for example, in this particular state, from this particular state, I might have a bunch of different tasks that I would like to do. Maybe I would like to either grab the cereal bowl, or maybe I would like to move the banana to the fruit basket. And conditioned in this state, I might need to follow different latent actions depending on what task I'm in. And with like a small, like 2-degree freedom latent action, I wouldn't be able to differentiate between these. Remember, the only reason latent actions would work was we were conditioning on a particular task that would really limit us to like how many tasks we can do with how many degrees of freedom in a particular given state. But one interesting thing that one could do is to try to use other types of modalities like language, right? Like if I provide language instructions, that is a way of disambiguating between these two different instructions. And I can still use my 2-degree freedom latent actions. I don't need to add more degrees of freedom. And language in some sense is acting as another degree of freedom. Like it's basically trying to allow us to disambiguate which one of these types of tasks we are interested in doing. So the question is, if I have these language instructions, how can I adapt my model to be able to capture them? And the first question you might be asking is, well, why are we even using language to start with? Well, first off, language, natural language, it's a very natural and expressive way for the users to give these instructions that allow us to disambiguate between these different states. And if you think about where the state of the art in robo-NLP is it's often something of this form. So robo-NLP, which is robotics plus NLP, is basically trying to oftentimes come up with fully autonomous policies where there's a user providing some sort of instruction, you have a state, you often have simulated scenes. And what you would like to do is you would like to generate actions based on that instruction, given that you're in a state. And you have like this black box that is trained on a giant amount of data to be able to generate some action. Okay. Most of prior work in this domain is either in like instruction navigation domains, and it's very limited. So oftentimes like these types of prior works require giant amounts of data. And then they often rely on, like, for example, in this navigation domain, they often rely on discrete actions. So there are usually like these discrete graphs with nodes that you can jump from one to the other. And here, like you can give the instruction of go left, and then based on that instruction, then you're going to like map that to the particular action that corresponds to going left. You often also rely on like simulators in these domains. There was a recent paper that actually came out of Google Robotics this past 2 weeks ago, I think. And there they were looking at manipulation, but it was huge amount of data for very simple tasks of like basically doing like moving blocks around. So they were looking at a very limited domain of like a block world environment, and then using large amounts of data to do imitation learning. So this is just to get to the point that robotics and NLP, if you're taking this particular approach, is oftentimes very limiting because it requires a large amount of data, requires simulation, requires discrete action spaces, can only work in navigation. The setting we are in is these manipulation settings that we have been talking about. We have a continuous control problem. We have this issue of the errors can accumulate. We don't have good simulators. And in general, in these types of domains, these types of the models that prior work in NLP you look at just would not scale up and would be pretty difficult to use them in these domains. So the insight here is let's not do full autonomy, right? Like why would we try to like find this black box when there is a person sitting there, right? Like when there is a person sitting there and can guide the robot to actually like help the robot like be more effective in doing what it is doing. So basically the key idea is let's use language along with latent actions, along with some level of shared autonomy, so we can actually achieve like these types of complex manipulation tasks that we are interested in. So the setting that we are looking at, it's called LILA. It's language-informed latent actions. And it's actually very similar to before. What we are doing is we have the same encoder-decoder architecture as before, but now we are including these language utterances use into the encoder and decoder. So we are conditioning both the encoder and decoder on the language instruction. Okay. And once we have that, then again, at test time, there's a user coming in and providing the language utterance, as well as these low dimensional action spaces. And that actually allows us to disambiguate, be able to do more interesting tasks, but also still use like a low degree freedom action space and do complex manipulation with language, which we weren't able to do before. Just to dive a little bit deeper in this idea, so the way we are collecting our data is extremely low data regime. So we collect 30 minutes of kinesthetic demonstrations. So oftentimes, like again, these types of imitation learning models, they often require a giant amount of data. We have 30 minutes of kinesthetic demonstrations. Then we replay the videos of these demonstrations to users on Amazon Mechanical Turk, and we ask them to describe the behaviors with language. So that's how we are getting our natural language. We're just showing the videos to users. We're asking them to describe the behavior. then based on these training exemplars that we are getting from Amazon Mechanical Turkers, we're using the distilled Roberta model with mean pooling to actually be able to do similarity search between these different instructions that are given. And at test time, when a new user comes in and says, grab the serial pull, then we use the same distilled Roberta model to actually get an embedding of representation of this behavior. And we use similarity search to figure out like what instruction is that closest to it. And we're basically incorporating these language utterances in our decoder using a film layer. So we are basically using a very standard like film layer here, where we are including the scaling factor and offset factor. And that is how we are incorporating the language information into the decoder. We are not like augmenting the state with the utterances. We are fusing that inside of the decoder when we are training this autoencoder. So based on that, if you look at Lila in action, this is some of the behaviors that you're seeing. So this is based on 10 demonstrations, like an extremely low data regime. We're looking at pour out the blue cup into the mug. And on the right, you can see the joystick inputs of the user. So up and down and left and right. And we're actually able to do this fairly like a complex manipulation task using language and again, joystick input, but joystick input is low dimensional, so not that difficult. If you compare the same video with imitation learning will not work with 10 demonstrations. So instead, what we did was we have 30 demonstrations for imitation learning. We do 3x augmentation on top of that. So imagine like 90 demonstrations. And from 90 demonstrations, then this is kind of like the behavior that we get from imitation learning, which is still like extremely not successful. And part of the reason is it's expected, right? Like in the low data regime, these robots can very quickly fall out of distribution. We are in an OOD state. And when we are in an out of distribution state, right? Like we need to figure out how to recover. Imitation learning would not be able to recover. And the whole reason that these transformers are working like so wonderfully is oftentimes like we have giant data sets, and robotics, we don't have giant data sets. That is the problem. If I had giant data sets, imitation learning would have probably been working okay too. All right, we also ran some user studies here, so I'm going to skip some of these. Let me just get to, because I do want to get to some of the other stuff too. So some of the key takeaways here is that we are learning a language condition policy that is basically helping these latent actions, guiding these latent actions to disambiguate between different types of tasks. And that gives us this kind of like intuitive paradigm of the user providing data and the robot in a shared autonomy fashion be able to like follow those instructions either in language or in a latent action domain. So there's a question on chat. The robot has 3 degrees of freedom, X, Y, Z. The robot has 6 degrees of freedom. So it's X, Y, Z and yaw pitch roll of the end effector, because the robot can like turn, right? Like it can also, also has the angles. So one way of representing like the robots, the robot is using like this end effector pose, X, Y, Z, and yaw pitch roll, and you could control the end effector. And based on how you're controlling the end effector, you can basically do inverse kinematics and figure out what the joint angles of like all the joints of the robot should be. Another way of doing that is to just provide joint angles, right? And that robot, if it has 6 degrees of freedom, then it has 6 joints, and you need to like provide those joint angles. If it has 7 degrees of freedom, then it has like 7 joints. A human arm has 7 degrees of freedom. So oftentimes, if you want the robot to do these more like complex dexterous manipulation tasks, you actually need to get like those angles too. All right. Okay. All right, so that kind of like brings me to the end of like this section, this first section, which was, it turned out that if I wanted to do this task autonomously, feeding autonomously, that is very difficult. I can't really write down a policy, a model-based policy for it. Learning doesn't seem to be doing the thing. So I should just teleoperate, but seems like teleoperation is also difficult. So what we did was we used learning as a way of learning a shared autonomy paradigm where humans can use language, latent actions, and still control the robot to do complex dexterous manipulation. In the second section, what I want to do is I want to talk a little bit about learning a fully autonomous policy. And I would like to basically try to tap into other sources of data beyond expert demonstrations, because as I showed earlier in imitation learning, I was mentioning that the only way of getting that to work is to give it a large amounts of expert demonstrations. And in general, collecting expert demonstrations is pretty difficult. Like we looked at this task of assistive feeding, like it's really difficult to collect lots of expert data here. And in many other robotics tasks, we usually have the same problem. Like you need to have like specific like devices. Maybe you need to have a VR system to provide data on your robot. And even like then, like the data that you'd provide using VR is oftentimes is pretty noisy and has like all sorts, you need to do all sorts of post-processing on that data. Or like you'd imagine that you have a simulation environment, but then you have to worry about the same to real gap. So just generally collecting expert demonstrations is challenging. So the question is, could we tap into other sources of data? And I do think we as humans do that all the time. Like if you think about a human learning how to like take a piece of food and like transfer that to their mouth, sure, they rely on expert demonstrators to some extent, maybe their parent or like caregiver, like they would show them how to like move their hand. Maybe they would provide even like kinesthetic demonstrations. But I don't think that is the only way that we use to learn how to like feed ourselves. We rely on other sources of data. For example, like we might be looking at like play data, right? Like when we are a child, like we play with our food, and you should not underestimate like how important that behavior is. When you're thinking about play, unstructured play, we are exploring like the whole state space. We are exploring the dynamics of the food, and we are learning so much about the environment and the food and how to interact in this environment. Sure, we're not acting towards an optimal policy, but we are learning quite a bit about the whole state space. And that's a very interesting source of data that I really think would be really useful in robotics too, and we should try to tap into that more often. So that kind of brings me to this direction that we have been exploring, which is around learning from play data. So what is human play? So human play is unstructured, undirected, multitask demonstration. So if I have this robot, I can teleoperate this robot. And what I can do is I can basically in an unstructured way, like move this block to like anywhere, push it, pull it, move it up the platform, down the platform, and basically provide this type of play data. Why is that good? So one reason that is useful is it's actually very scalable. It's very cheap to collect play data compared to imitation data. Part of the reason is if you want to collect like expert data for imitation learning, I need to define what a task is, right? Like I need to actually define what pushing is, right? I need to write down a reward function for that. And pushing is really simple, but like if I'm trying to like open a drawer, that's a slightly harder. Or if I'm trying to do, I don't know, like open the door of the microwave, I need to actually write down a task, like a reward for that. I need to train a policy, an optimal policy that can actually like do the task so then I can collect data on that task. So it's a little bit of a chicken and egg problem too. If I had that policy, then why did I even like need data like on this particular task? So oftentimes writing down task specifications, reward functions, reward design is pretty difficult. But in play data, you don't need to have any task specifications. You can just like move around like randomly and interact with the object in this environment, and that's perfectly fine, right? Like if you fail at this task, whatever, you've just like collected like some amount of play data. The other reason that this is useful is that it's reset free. So if again you go back to like the expert data, if I want to collect expert data on pushing a block, I push a block and now the block is pushed. So now I need to reset the environment so I can like push the block again. So in general, if you look at like robot learning labs, when they're trying to like collect these types of data on real robots, they often have a second robot that resets the environment for the first robot. So when you're doing data collection in robotics, you often need two robots, the second robot just resetting the environment for the first robot, which is kind of crazy and silly. But again, if we go back to play data, it's reset free, just continue from wherever you have left off, right? You don't need to like reset the environment. And all of these are like reasons for making these types of data a lot more scalable than any other type of data that we could leverage. In addition, with this type of data, we are going to have a broad state action goal coverage. With expert demonstrations, you only see one like initial state, final state, like your goal state, and a sequence of actions that takes you there. But you don't necessarily get an exploration of the rest of the state space. And this exploration can potentially help with learning more generalizable and robust policies. So if you fall out of distribution, you have seen that state, you can come back in, and that is really like useful. And also it helps us to have access to human priors on goals and behaviors. So generally, I'm advertising play data a little too much, but I do think it's a very useful source of data that we could actually leverage. So now the question is, how do I learn from play data? Let's say I've collected my unstructured play data. How do I go about learning from that? So the thing is, you could actually view play data as object interactions. The key insight that we have is that play data, it's this long sequence, right? Like this is like, it's a giant long sequence of interactions with the world. And if you pick any window of play data, it has some pre-interaction phase where like the robot, for example, is moving towards an object. And what we are defining as an interaction phase is when the robot is making contact with an object, right? So the robot makes contact with an object and the object is being moved. And I'm going to call that region an interaction phase. And in some sense, there's a post-interaction phase where the robot retrieves away from the object. And you can really think of this post-interaction phase as the pre-interaction phase for the next play like sequence that we are looking at in this giant like long sequence of play data. So if we segment our play data based on this idea of object interactions, we can have a lot more like we can have a lot more focused way of thinking about like these different affordances that occur here, like the object being pushed. So the key idea is get your play data segmented using object interactions, using this idea of when contact is being made. And once you do that, you could sample an object goal state from this post-interaction phase. And you can take your interaction phase and you could encode that interaction phase into a low-dimensional latent representation similar to before, but now we are representing this whole like interaction sequence into a low-dimensional representation that captures affordances, like the fact that object is being pushed. Like this representation is capturing the notion of object being pushed. And what we would like to do is we would like to learn a policy that is conditioned on these affordances as well as the goal state. So this is the high level of the algorithm and what we are doing. Sample a goal state from post-interaction, represent your interactions using a low-dimensional representation Z, and train a policy conditioned on Z's. Okay. To get into like a little bit more detail of what we are doing here, let's just talk about that a little bit more. So I mentioned that we can take the interaction phase when the object is making contact. So let's call that tau I. So this is for interaction phase. What I can do is that in training, I can take this data and I can try to encode that into a low-dimensional Z. And this Z is really capturing these affordances that I'm referring to, like the idea of object being pushed or being lifted. If you actually look at the TSNE of like these Z's that are being learned, they separate. They separate based on like the type of task that is being performed in that particular play data. So in addition to that, what we would like to do is we would like to train another network. I'm going to call that E prime. And E prime is basically trying to match this network E as closely as possible. So I'll define a KL loss that tries to get this Z's as close as possible to Z prime. And the reason that I'm training E prime is that at test time, I don't have the play data anymore, right? Like training, I have offline play data. From the play data, I can figure out what the affordances are. But at test time, I don't have that. The only thing I have access to at test time is my initial state and some idea of what my goal state should look like, what I'm trying to do from this initial state to the goal state. So what I would like to do is I'd like to be able to identify what are the affordances that are necessary to get to this goal state at test time. And for that, I need to train this other network that matches this encoder at the top as closely as possible. So that's my first loss. I have a second loss here. And the second loss, basically the idea of this second loss function is to sample an affordance, a Z, from this encoder, and then try to train a policy, so almost like a decoder here, that is conditioned on this affordance as well as the goal state that is coming from here. And what we would like to do is that this policy or decoder is basically generating actions. So we have a reconstruction loss that is making sure that we are reconstructing the same actions that we are seeing in our play data. So that is basically the training that we are doing. We have a KL loss and we have a reconstruction loss. We are training 3 networks, an encoder that gives us low dimensional affordances, a decoder that gives us the policy, and another encoder that's trying to match the affordances that we are learning. So at test time, we are just using E prime and pi. In training, we are training for E prime and pi. At test time, we are just using E prime and pi. And that is how we are learning from play data. All right. So let's see what we can do with this type of play data, with this type of training, right? So this was my training. Let's see how that works in practice. So here's a simple 2D environment where we have some amount of play data. We are looking at pushing or pulling, lifting an object, maybe tipping it over. Side rotate is actually pretty challenging. Like you're moving it and side rotating it. And here we are actually randomizing block sizes, masses, positions. This might seem a simple environment, but the fact that we are like randomizing so many physics information, like in the simulation, it actually makes it kind of a difficult domain to play around with. And we are comparing our algorithm with Play LMP, which is a prior work on learning from play, which doesn't like think about object interactions or learning affordances. Instead, they just learn like latent plans. They don't learn affordances. And then we are looking at goal conditioned behavior cloning as another baseline. So if you look at PLATO, our algorithm, compared to these prior works, all across, even on these simple tasks, we are outperforming prior works. This is with scripted play data. We could also try human-generated play data, and with human-generated play data, again, same story is true. One interesting point here is that human play is like human data in general is so different than robot generated, like scripted data. So here, like you're looking at these very simple tasks like pushing or pulling. And like we thought, well, how different would it be for me to script the data for like pushing versus actually like push this block in simulation? And it turns out that it's very different. So the model that we trained on scripted data, it was working like wonderfully. And like 1 week before the deadline, we were like, okay, like might as well like try this on like human play as well. And like we tried on the same amount of human play, the same model, and it actually did not work at all. So it's very interesting because human play and human data in general has a lot more variability. So because of that, we needed to collect more data, we needed to tune our hyperparameters, and we needed to have a slightly more expressive model to be able to capture like learning from human play data. It wasn't that easy to get the second results working. And even then, right, you can see some of these results have much lower performance compared to the case where we have scripted play data. So the reason I'm mentioning this is I think this is an important point that roboticists don't talk about as much. They say, oh, you collect expert data and you just run your algorithm on that. But expert human data is very different from like other types of data that we collect, and it does have all sorts of biases in it. And people do all sorts of post-processing like after the fact to make the data clean. But what does it mean that we are cleaning the data? And like, why, like, is it scalable to clean the data? So in general, I feel like we need to have like much better approaches to go about data curation and talk about quality of the data before just like throwing data at the model and hoping it would work. All right, so moving forward, we have also looked at a number of like more difficult environments. So you can consider 3D environments. This playroom environment is like you're moving blocks around, like opening, closing drawers, cabinets. Let me just move to that because I think that is probably the more interesting thing. So yeah, so here again, like we are comparing PLATO with these two different approaches. And again, all across, you can see that PLATO is outperforming some of these other approaches in some settings more than others. In general, in more difficult tasks, like sometimes in more difficult tasks, the gap is much larger. Like for example, for drawer close, we can kind of like see that the gap is much larger when we have like play data. Again, like this is because we are leveraging these affordances and we are leveraging the state coverage that we get with this play data. And some of the tasks are just like pretty difficult to all over. We did not actually collect real play data. One thing that we wanted to play around here is to collect real play data and try to train a policy in real. We haven't got a chance to do that yet, but we have shown some level of transfer. So if you train this in a simple environment like block pushing, you can actually show that the same policy transfers to real, and we see similar types of gaps when it comes to just like using the same policy in real. All right, so what are some of the key takeaways here? So the key takeaways is that, well, we're using PLATO, and the idea of PLATO is to intelligently segment play data based on object interactions, based on the fact that we are making contact. And this type of segmentation helps us to learn affordances, low-dimensional latent affordances, and really leverage those affordances to learn robust generalizable multitask policies that can tap into this other source of data, play data, that would be, I think, really powerful in addition to like imitation data that we often rely on. All right, so we talked about expert demonstrations, the fact that not always we don't have access to them. And we talked about play. But there are also other sources of data. And this talk is really trying to like get at the fact that we need to tap into these non-traditional sources of data. And one of these other sources of data is suboptimal demonstrations, right? So for example, you might have like other agents who are also trying to like figure out how to eat. And maybe they're not very good at doing what they're doing, but a lot of times like we observe them, and by observing them, we learn something useful about teaching. And the question is, could we tap into suboptimal demonstrations? And could we try to learn something useful from suboptimal agents? So I'm going to briefly talk about this, given the time. I don't want to go into too much detail around this idea of learning from suboptimal demonstrations. I just want to get some of the key ideas around here. So basically, in the setting of imitation learning, right, like we usually don't have any reward information. We usually assume no access to environment dynamics. We usually have data sets, offline data sets of expert demonstrators, and we just do supervised learning, pretty much like it's a supervised learning problem, where we learn a robot policy from these trajectories. The question is, if I have suboptimal humans, if I have agents with varying levels of expertise, could I still learn an optimal policy from that without access to reward information? So that's kind of like the key part of it. I don't want to assume I have access to reward, because if I have access to reward, of course, I can tell someone is a novice player and someone is an expert player. Without access to that reward information, can I identify who's an expert, who is a novice, and try to learn from them? That is kind of like the key idea of this section of the talk. Okay. I want to just give the high level idea of this in a simple example. So I'm just going to go over that simple example real quick and then wrap up this section. So what we would like to do is we would like to define expertise to be a probability that tells us how good an agent is in a particular task. So if this row is probability of succeeding in a task, if that row is close to 0, then we know we have a novice player. If it's close to 1, we know we have an expert in doing a particular task. We don't know what those rows are, but if we knew what the expertise is, then the problem would become really simple, right? Like I could just do like a weighted imitation learning approach here, like weighted behavior cloning, and based on this expertise, I can just like weigh the demonstrations coming from each one of these agents based on that, right? Like if I know the expertise of this agent is 0, I don't trust anything they say, and if I know the expertise of this agent is 1, then I'm gonna like highly trust what they are saying. Okay, so that is what I would do if I knew the expertise. Okay, so let's look at a very simple example. The simple example is that I have shapes of different colors. Let's say the task, the action is to tell us like what the color of a shape is. So like the optimal expert agent is going to set red, but maybe like a novice player would say brown when they see like a red square. Okay, so we said, well, if we have the expertise, so let's say we have expertise of these agents. If we have the expertise, we could do a weighted sum. So I'm just showing here that if you do majority vote, that's a bad idea. But if you do weighted sum, a weighted vote, then you're going to actually get the right answer for each one of these. So here, maybe I have, let me just demonstrate, tell you what this table is about. I have a bunch of states. So maybe I have a red square and a black square, and I don't know, different shapes, different colors. I have agents who are going to tell me what is the color of these. This is my data. So think of the columns as my data. I have a novice player who's just absolutely wrong. I have an intermediate player who's like 20% right, 60% right, and I have an expert who's always right about this. If I do majority vote, that's a bad idea because I have like 2 like really low like novice players who are going to tell me, for example, that the color of this black circle is brown. And if I do majority vote, then I would think this is brown. That's a bad idea. If I do a weighted vote, then great. Like I have expertise, I would be able to recover. The setting that I'm in is I don't have these expertise. I also don't have any rewards. So the question is, how can I recover the expertise? So the key idea of this approach is to take an iterative approach to identify the expertise and the policy like at the same time. So at the high level, what we would do is we would start doing majority vote, which was that bad idea because it would think that this guy is brown. But based on this majority vote that we are doing, we're going to go back and update the expertise. So we are iteratively updating the expertise and policy, right? So I did majority vote. I now think the policy is what I see in this last column. I'm going to go back, and based on that, I'm going to update the expertise of what I think the expertise of these agents are. And when I do that, I realize that this novice player is actually a novice player, right? Like I realize that the expertise of this agent is 0.2, and like it's pretty low. So now I can do a weighted sum with these new expertise values, and I get a new policy, and then I can go back and update my expertise. So that is the high level of what we are doing. It's not going to always work, right? Like if I have an adversarial agent, it's not going to work. It's only going to work under some assumptions. And I'll talk about those assumptions in a second. So what is the idea here? So we are doing imitation learning, and the way we are doing imitation learning is we have agents with varying levels of suboptimality, and we know who the data is coming from, right? Like we have demonstrators' identities. So in some sense, I can go back and say, well, this data was bad data. It was coming from this particular demonstrator, and that demonstrator had no idea what they were talking about. So I am going to downweight them. So the idea, one of the assumptions here is that I actually have access to demonstrators' identities. Okay. These are some minor points, like this could be state dependent. So I'm going to skip the state dependent idea. So more formally, what we are doing here is we are trying to capture this idea of expertise, right? This row value that I was getting at before. This is probability of you succeeding or not. And this probability depends on two things, depends on what task are we talking about. So we're going to have a task embedding. So this F function is just a task embedding, a function over state parameterized by phi that tells us like which are the relevant like skills that are needed for in this particular state. And then we have a proficiency vector, so omega, and omega here is basically telling us how proficient you would be at each one of these skills. So imagine that I have these skills, and then this F function is telling me what those skills are, like which one of those skills are needed at this particular state. And omega is going to tell me how proficient this particular user is at each one of these skills. So you can basically take the inner product of that, and that gives us this expertise. We can, of course, like take a sigmoid on top of that just to make sure that gives us a probability. So the idea is that if your skills and your proficiency are aligned, then you have high expertise, right? Like if they are aligned, you have a high inner product. Take a sigmoid of that, that basically tells you you're closer to being an expert. And if they're uncorrelated, then you have a novice player. So this is the model that we are using for expertise, okay? So then based on this expertise model, this is the big assumption that we are making here for the story to work. The big assumption that we are making is that we're saying the policy of these agents, the model that we are going to use for policy of these agents is going to take the correct action with the expertise, probability of expertise. So if you're 60% an expert, then you're going to take the correct action 60% of the times. And you're going to take the incorrect action uniformly at random across all the other actions, which is an absolutely wrong model because that's not how humans work. But the reason that we are making this modeling assumption is for theoretical reasons, right? So if I make that assumption that you're either taking the optimal action with your expertise probability, and then you're taking suboptimal actions, they are going to be uniform across everything else. That way I can actually be able to recover the optimal policy, because the suboptimal policies are not going to have enough signal. The signal for the suboptimal actions is going to be diffused across all these other bad actions. So I'm not going to see like particular like signals from these suboptimal actions, and I should be able to recover my optimal policy. So that is the reason we are making this assumption. This, again, would not work with adversarial agents, right? Because adversarially, you're not going to uniformly take a bad action. And as I was saying, this is not realistic, right? So of course, this is not going to work. Like, of course, this is not an assumption that's going to hold on realistic data sets. But the interesting thing is we have actually ran experiments on real data sets. And even though this assumption doesn't hold in practice, this algorithm is still like actually able to like give us policy that's very close to the optimal policy. So I didn't tell you what the algorithm does. The algorithm is really simple. The algorithm is basically just optimizing for maximizing the log likelihood of the data that we are seeing under this assumption. So basically I have a policy parameterized by theta. I have phi, which are parameters of my state embedding, because I'm capturing like a state embedding. And then omega here is representing proficiency. So you can think of phi and omega representing my expertise. And then I have some amount of data, suboptimal data. I'm just trying to optimize the log likelihood of that data. That is all we are doing here. All right, I'm going to try to wrap up given the time. So let me just go to some examples where we tried this. So we tried this across a number of examples. There's this mini grid environment where we had some fake data, and this this was under our assumptions. So we generated data under the assumptions that we are putting on the algorithms. The key idea of the mini grid is that we have agents for different tasks. So I have an agent who's really good at doing this lava task, and I have another agent who is really good at doing this unlock task, but like they're bad at other things. And if I have data from both of these agents, could I still learn how to solve the lava task and unlock task? And it turns out that we can. The other two data sets are real data sets. So RoboMimic is a robotics data set of real human data of varying levels of expertise for doing tasks like moving the square on the peg. And then the last data set, it's a real chess data set. In this last data set, we are not learning the policy, we are just learning the expertise. But this is the Luch's chess data set of real like human players playing chess who have different ELO ratings. So across on all of these, we basically see iLead outperform like behavior cloning on all demonstrations or best demonstrations, even when we have like data coming from agents with suboptimality. So it's interesting, we get like 70% success rate in these settings where we have agents like who are only an expert in one task, but we actually get like high performance across all tasks, like at around 70%. Okay, I'm going to skip a lot of these. And then similarly, we see good results across all of these environments. All right.
Yeah, Dorsa, just a quick question. This is really interesting that you have such a great performance in practical situation. So, is the underlying assumption behind the algorithm, is it that the majority should be more or less correct, and then based on that you propagate signal back in order to understand? But if majority is incorrect, then you may basically flip, right? So you may think that the non-expert users, they're experts and vice versa.
That's exactly right. Yeah, that is the assumption that we are making. And the hope is that in realistic data sets, right, that would be the case, right? Like in these robotics data sets that we are looking at, people are not trying to be like adversarial, they're actually trying to be right, but they have some level of noise and we just don't know like what that level of noise is. So for the type of data sets that we are like looking at, this type of assumption like actually like holds like in practice. But yeah, you're absolutely right. Like the idea is that you're getting most of your signals from the correct actions.
Thanks.
Yeah. All right, so let me try to just wrap up because I want to like leave like we have 2 minutes.
Dorsa, we have the room until in your time 1:45, so we have the room like for 15 minutes.
Okay,
so,
wonderful. All right, so but yeah, let me just try to quickly like go over like, because this last part I just wanted to like show some ideas and like directions that we are looking at, so it's not technical, and then I can take questions after that. All right, so what have we talked about? We talked about assistive feeding, the fact that that would be a wonderful problem to solve, but it is difficult. We don't have model-based policies for it. We don't have learning-based policies for it. All we have is teleoperation, and even teleoperation fails. So what we did in the first section of the talk was provide latent actions, language-based latent actions, and to make this teleoperation easier, but be in a shared autonomy domain. There is still a human providing some input, easy input, but some input. And then in the second part of the talk, we started kind of like tapping into all these other sources of data, right? Like we talked about play and the fact that play gives a lot of coverage over states and actions. And then we also talked about suboptimal demonstrations, the fact that realistic data sets are not like fully optimal expert data. They're all over the place. And maybe they're not adversarial, but they are not perfect either. And we could actually tap into these other sources of data and try to learn like policies that could learn from them. Actually, maybe given that we have like a little bit of time, let me go back to this result of like this RoboMimic data set. So this RoboMimic data set is interesting because this is real robot data, real human data on a robotics task, like moving a square on a peg. And we have 2 players who are like really good at the task, 2 players who are medium at the task, and 2 players who are not good at the task. And we are comparing this algorithm, iLead, imitation learning by estimating the expertise of demonstrators. We are comparing that to offline RL. So this is an offline RL algorithm, IRIS, which actually assumes access to reward labels. We did not assume access to reward labels. And we're also comparing that to BCRNN, which is kind of like state of the art for like behavior, like imitation learning in some sense, because it is capturing some level of history. So it's having an RNN architecture on top of behavior cloning. And we see like across all combinations of these, we're seeing like fairly good performance and higher performance than these 2 offline RL and imitation learning approaches, because we are actually able to recover these expertise values and figure out who to trust to be able to learn how to do this task. And I think that's in general like pretty exciting, like the ability to like tap into like data of a data set that does have like really bad players and okay players and still be able to learn something useful from that, I think is pretty interesting. All All right, so let me go back here. All right, so the last section that I wanted to just very briefly mention is this idea of assistive feeding, right? Like that is what I motivated the whole talk about, and I didn't show anything on assistive feeding. And the reason it is hard, right? If I were to use like these learning-based approaches, like on assistive feeding, it is still pretty challenging. We have not collected like play data on food yet, and in general, like even suboptimal demonstrations, it would be really difficult to collect large amounts of that, like on these real robot data sets. So something that in general we are looking at is to tap into like things of the form of videos or like other types of offline data sets to be able to better learn policies. So that's something that we are working on in the lab. But more specifically on the assistive feeding problem, one could really try to, like, again, take a model-based perspective to it and try to just like solve that. If I wanted to just solve assistive feeding, there are two components that fall into play. One is acquisition. So how do we pick up food? And the other is food transfer, like bite transfer. How do we transfer it to a person's mouth? And both of these are pretty difficult. So the reason that acquisition is hard is here are some videos of why it is hard to pick up food. So let's say that you have a policy and it's, let's say, parameterized policy then. For example, if you're trying to pick up a grape, it might roll over, or you might be able to like skewer the food. Like, for example, in the case of the cherry tomato, you're going in, but you just like don't have like the right forces or the right angle. Your fork might break if you're trying to like pick up carrots. Bananas are extremely hard. They keep like falling out and like being shooted to different locations on the plate. So in general, it's pretty challenging to do food acquisition. So something that we have looked at recently is to leverage visual and haptic information to rapidly and reactively plan these skewering policies. So we are using haptic information, like the forces, to figure out the deformability of the object. And we are using like visual information to actually like be able to figure out the shape of the object. And the interesting thing is, based on the deformation, that is the thing that can tell you like what your fork pitch should be. And based on the geometry, you can figure out what your fork roll should be. So you actually get some information about these angles of the fork, the angles that your robot should actually execute based on the deformability and geometry of the object. So we have a parameterized policy, skewering policy, that is able to use this information like in real time, like it's basically filling the forces, and you can see the force information on the left. It finds the right place, the skewering point based on the visual information, and it's able to like pick up like a variety of food on seen and unseen plates. So we have actually tested across all of these. But I think in general, this is a very exciting direction to actually like push on. And then on the bite transfer side of things, that's also very interesting. So the question is, how do we do transfer in a way that is not jarring and weird? And one thing that we have done first is, before even like worrying about transfer, there are design choices that one can make. Like, for example, if we have, like when we feed ourselves, it's not that we are feeding ourselves with a full arm. We have a wrist. That wrist has a lot of use. So the first thing that we did was we actually like worked on creating this this fork that has like another joint that allows us to kind of like have this notion of wrist that makes things easier for transfer. It turns out that this fork is also useful for other things. So with the wrist, we were able to like add this twirling motion and be able to pick up things like spaghetti, which is pretty exciting. So we are looking at figuring out ways of like grouping and twirling spaghetti and picking things up with this new fancy wrist that we have. And then in addition to that, when it comes to transferring the food, again, using this wrist and using parameterized policies that have varying levels of reactivity, we were looking at the transfer of the food to people's mouth. Again, this has like different levels of reactivity based on the forces that it feels when the food is being transferred, when it's entering the mouth versus also like when it is getting out of the mouth. So there are a lot of like detailed challenges when it comes to these real robotics tasks that need to be addressed before like me throwing learning at it. And I just wanted to like briefly touch upon some of the real challenges when we are thinking about like bite transfer. So with that, I'm gonna stop here and thank the group, and thank you guys for listening, and I can take any questions.
Fantastic. Let's thank Dorsa for kind of amazing talk. We have time for some questions. Yes, go ahead.
Yeah, so when learning from play, can you basically just drop an uninitialized agent into some space with some rules and expect good results? Or like what kind of initialization do you need to do before play can happen?
Yeah, so we need to have like some almost like subtask like policies of moving objects around. So you can initialize it at any point really. And then if it is human play, like if it is actually human play, you don't need to like do anything, right? You just like initialize the robot wherever and let the human like follow their heart and like provide data. And because they have the right biases, they are going to like take the robot to interesting places. So that is why play data is useful, because the human, it's not random data. The human like basically takes the robot to the right places of the state space, and that is like a good way of collecting the data. For the scripted data that we have looked at, we have scripted like sub policies like pushing or pulling, or like these different types of like sub policies that you could do. And then we have just initialized it from like one particular point in the state space and just like basically rolled out these different policies at various points, the scripted policies. Yeah, potentially one could come up with better ways of like generating that data too, but that's how we collected our scripted data. Yeah.
Okay, Furang, please go ahead.
Oh, thank you. Thank you, Dorsa, for the wonderful talk. I just have a very quick question. So it seems like assistive feeding is something I would really care because I'm a mom. And I care a lot about the safety, of these robots. Do you have any comments about, what other future directions for our research to guarantee that robots are very safe?
Yeah, I think it's that's a wonderful question. Also, I care about assistive feeding for feeding kids too. That's something that I care about as well. But yeah, in general, like safety is kind of like a big issue here. So in general, there's a lot of work in the space of formal methods and robotics that is trying to like get at safety critical, like safety critical questions and being able to give guarantees for robots. Usually, like a lot of these works, I often see them in the space of autonomous driving and those types of directions. But this is a perfect application to demonstrate like formal methods, like actually like working in these domains. And part of the reason that I feel like it is hard even for those domains is oftentimes they define safety by collision avoidance. And here I do want to make collision with the person's face. I actually want to put some force. I'm making physical contact with the person. So now the question is, what is the right physical contact? Like what is the right amount of force that I should put in? We haven't looked at the safety of this closely. All we have done are pretty much like engineering things to make sure that it is safe for the user studies. So for example, like we tune the amount of reactivity. There's a giant red button right there that the user can like press at any point in time. We let our users like wear glasses. We make sure that we like have like multiple sensors that tell us like a state at any point in time, like so we have some level of redundancy. So we're doing all these engineering things to make sure that this is safe, but safety is a huge concern here.
Yeah, thank you. That's very interesting talk. Appreciate it.
Of course.
There is one question on Zoom. It asks, could you please elaborate more on the arm and configuration you're using for haptics?
Yeah, so that's a good question. So what we are using here is a Panda Franca Amica arm. It has 7 degrees of freedom. It does have like it does have like force sensing by itself, but in the feeding case, we are adding a force which is mounted, like the force has an additional force sensor on it. So we have a force sensor on the fork that is actually like giving us this haptic information. I don't remember the exact details of the force sensor, but there is a fancy force sensor on the fork that is giving us like the force information when the person is like biting on the food that is coming directly from the force. Yeah.
I have a question myself. In the last part, that was very interesting. So I was wondering, like, in terms of like, understanding the texture of the food and like, what kind of force we need to apply. So is it possible that, for instance, we, deploy a classifier or an object detector and to basically, see what kind of foods, we are grabbing, and over the time, we learn what is the proper force for this object, right? So if I'm eating a banana, maybe at the beginning I'm like going to apply a lot of force and that doesn't work, but then I'm learning over time with more try that what is the appropriate force for the grabbing the banana is. And then later on, if my object detector says, okay, so there's like banana in this table, in this plate, then I can go and look at the prior knowledge I have and I use that.
Yeah, no, that's a great question. And I think it would be interesting, yeah, to do that. So the works that are doing this right now. So our work basically, like we collect this data offline. So assume that we have some, like we take a supervised learning perspective to it, right? Like we collect the data and then based on that, we like do this classification. We do the classification in an online way, but we are not doing any online learning or adaptation. So the idea is that the fork is making contact with the force and with the food, and based on the force that it realizes like what the force is, it changes its angle. So it's like, oh, it's a tough banana versus it's a soft banana, and it changes that angle like on the go to pick up the food. There is another work from Tapo's group at and Sid Srinivasa's group at UW and Cornell, and what they are doing is they're doing a little bit of probing. So they probe the banana at the go at various like locations, and they actively do this. So they actively figure out where to probe, and based on that, they pick up the food. What you are suggesting is like maybe like more of an online perspective, that I pick up like some bad bananas and then I realize and adapt my angle. I think one can do that. There are kind of like practical challenges. You're gonna like mess up a lot of like bananas, so you need to like continue giving a lot of bananas to this robot. So there are kind of like these practical like running reinforcement learning on the real robot like type challenges, which basically like similar to the reset problem, right? Like you have to reset the environment. Now you have to like set up like the banana, the plate again. So if we could do all of these in simulation, that would have been wonderful, but like we just don't have good simulators for these types of things. Yeah.
Yes, fantastic. Let's thank Dorsa one more time.
Thank you. Thanks for having me.
Thanks a lot for such an amazing talk.
All right. Thanks. Okay. Hope to see you all again. Bye.
Okay.